in other modules we have shown like complete fabrication procedure, like from silicon wafer, then cleaning, followed by coating of polyamide layer or polyamic acid layer, and curing it to make a polyamide film. After that, lithography, then deposition of metal using electron beam evaporation system or by the process of evaporation, and after that lift off, and after that we, so basically that is like fabricating on electrode array, standard procedure of fabricating electrode array, that we are doing here. Now as we, I mean as we have already studied the things like sputtering, thermal evaporation techniques, like that, other PVD or physical vapor deposition techniques. So here in these modules we will demonstrate how the sputtering tool works, or how to do that sputtering system. So here we will demonstrate DC sputtering, RF sputtering both, and in consecutive modules we will show you the thermal evaporation as well. So here, as we are we do not have any particular device to fabricate for this, I mean or using this sputtering tool. So we will just do some sample deposition just to show you or demonstrate the things. Here from the, I mean this is just like a recap. We have already studied how sputtering works, or how sputtering tool works, how sputtering as a system, how it works in the theory modules. So coming to this module, this is just a quick recap. So here unlike the any evaporation technique, this is I mean here you do not have to melt the material and get the vapor or the evaporated thing to deposit the things. Here what we are doing is, first we have a substrate here, let us say we load the substrate, let us say here, and a target here. So target will be negatively charged. So as target is negatively charged, as you know that it will attract argon atoms. So here not argon atoms, argon ions. So here what we are doing, we will flow argon atoms here as a in gas phase. So with a high electric field it will break in ions, and that argon ion will fall or will be attracted to the target and hit that. So kind of scraping of the top layer of the materials will happen, which will lead to evaporation on the substrate. So this is how this works basically. So this can be with a DC source, this supply, or this source can be RF also. So here, as we have discussed already when we were discussing about e-beam evaporation tool, we have mentioned that there is a limitation of that e-beam tool, that we cannot deposit very high melting point materials. So for example, what crucibles we are using, those are of either molybdenum, or we can use tungsten also, or we can use graphite. So these are high melting point materials. So these we are using as, or was using as crucible, because those cannot be evaporated by the electron beam. That is why we were using as a container to keep the melt inside. So here let us say we have to deposit tungsten, or maybe we have to deposit molybdenum, or we have to deposit any other insulator like silicon dioxide, silicon nitride, or any other insulators basically. So here is the tool, the sputtering tool we have to use, because usually these oxides, nitrides and high melting point materials, these cannot be melt with that electron beam, and here the scraping of the materials from top and evaporation, that is basically the sputtering of any material. That is the only way to deposit it, or we have to go with chemical vapor deposition techniques that we will cover later, or we already covered the theory part. So that you can just check it again if you are not comfortable enough with this. but for PVD or physical vapor deposition techniques, this is the only way. So here is the sputtering tool. We will show first in the same way that what are the things or the different parts of that, and inside what are the components available. After that we will open the chamber, we will again demonstrate what are all components inside the chamber, and then we will load the sample and we will show how to deposit material using that. Starting with the components, like this is the first one. So this is the chamber. In e-beam evaporation tool also you have seen the similar chamber, but here you can see, here are the water flows that is required. So inlet and outlet. Inlet water with from a chiller, basically that is chiller outlet is inlet here. So that will be used for cooling down the magnetron. So here there we had electron beam gun, here we have the magnetrons. So this inlet water will cool it down, and here is little hot water, that is outlet from this after cooling the magnetron part. And here as you can see we have one viewport. So during deposition we can just open and see the things, but now as inside it is dark, so we cannot see anything, but when plasma will be created, that time we can show the things. This is the first part, our chamber. We will load the things inside, load the substrate inside, and the target will be there and we can deposit. So coming to this part, here first this is the display. So whatever operations we are doing, like let us say creating vacuum, let us say triggering plasma, gas flow, switching on gas flow, switching off gas flow, heating, all these things whatever we can do, we have to do it, we can give the instruction through this. This is a touch panel based. Here this is that like 10 button, like that it was in evaporator tools also. So this is for switching on the things, and this reset button for resetting the hardware after each and every use. This is again one of the most important part. This is that emergency emergency stop switch. So if you are in an emergency or if something happens, you can just press it, it will like auto cut the tool, and you can just open it before next use. Here is the thing. So here you can see, here this is the temperature controller, it is as it is written already. So when we will operate the tool, we will show you. So the top part that will show the actual temperature, and bottom here it can show what is the set temperature. So with this we can elevate the temperature, and at an elevated temperature we can deposit materials. So as I already mentioned that insulators can be deposited, insulators as well as the dielectrics, basically dielectrics can be deposited using this sputtering tool. So we may need to deposit the material at some elevated temperature, such as let us say around 300 degrees C, or maybe 350 degrees C, 200 degrees C. These are like the standard temperatures usually we use to deposit material sometimes. But if it is a metal, then usually we do not need any elevated temperature. However, if required, we have the provision here. Here this is the DTM, exactly the same thing that we have discussed in our electron beam evaporation demonstration module. This is exactly the same thing. So here these two are something different that you did not see or came across the things in our last modules. So here this is basically the RF source. So as I already mentioned, so just to give a brief about this tool, we have two magnetrons. One magnetron is connected to the RF source, and the another magnetron is connected to the DC source. So here this is the RF source. So we can control this from this display only. So we will just set the power, and the forward power, reverse power, everything will be automatically taken care by this module. This is the power source, power supply, and here this is the DC power supply. So if we see, we can just, it is always switched on, and here you can see 3 displays. So here 3 displays, 3 buttons to increase or decrease the values, and here set and read, like set and read, this change for each and every parameter. Here first what we usually do is, in this DC source, this can support up to 800 volt and 1.5 milliampere 1.5 ampere current. So we don't need 1.5 ampere current in most of the cases, we usually deal in milliampere range only, so less than 1000 milliampere. And here this voltage, so how it works? So basically you can see there are two modes, either set mode or read mode. So when we will switch it on, we will describe again in details. So read mode is basically to see how much voltage or how much power or how much current is actually being delivered. So that is in that we can see from the read mode. And when we press this in set mode, so basically the in set mode, if you can if you increase this or decrease this, so by that you can actually set a higher voltage or higher power or higher current. So usual procedure is you can first set on voltage on power here in watt. So whatever is expected for you, let us say now tungsten is loaded in DC on the DC magnetron. So here you can just, so what we have optimized, you can go till 200 to 300 watts, so you can increase it. So after switching on, obviously in set mode you can increase it, keep it there, place it at read, so you can see how much current how much power is getting delivered here. After that you can increase this up to 300 to 400 volts. So that is your initial and a steady voltage input. So after that you can just check the read, how much is getting delivered actually, and then you can set the current as required to match this expected wattage. So when that your set power will reach, it will be it will saturate there only. So after the set power you cannot go beyond the set power, how much ever you increase your current. So this is basically a regulatory thing. So here you can increase the set power and again use it at higher power if required. So usually we usually keep everything at read mode, so that whenever we will switch on something, it should not be automatically on and start giving some or start delivering some power. So this should be switched off, and this is also switched off already. So here we have checked these things. So here we have provision for like copying the recipes, or we can in auto mode we can just send send some recipes also from here using the USB drives. So this is the basic things that we have, and here already have discussed about this. Now we will just check what are other ports and what is there in this. So as we have seen this components, whatever is accessible from outside or whatever is visible from outside here. So after that we will open this, we will get a brief introduction about this just like the other components, then we will move to the next part. So let us open this. So before opening, you can just see here, before opening the door you can see here again the similar warning again like electrical hazard, that isolate main supply before removing this. So isolate main supply means better whenever it is switched off you can open this. It is not like you cannot open this when it is in action or when it is running, because this is a mechanical key, so you can open it anytime. But you should be aware that whenever supply is on, there is a fair chance that you can get electrical, you can get any hazard from here. So now we are demonstrating it when we are when the system is off. So I will go that side so that you can see this thing properly. So here you can see this is almost similar things that you have checked, and obviously just to mention it to you once again, this lock means this and this lock is connected to the safety interlock. So if this is on by any chance, it will be sensed by the tool and you will get an warning sign, and as long as this is on, none of these supplies like RF supply or DC supply to the magnetron will not be on. So it is mandatory to close all the doors, then only that high power systems you can high power components you can use. Otherwise basic pumps or basic transformers will work. So here if you can see, this is the same pump, rotary pump that we checked when we have demonstrated that e-beam evaporator system. This is the similar pump. So here it can go up to 10 power minus 4, or better to say 10 power minus 3 to 10 power minus 4 millibar range, as we have discussed earlier. And here we have one transformer at the right side, here if you can see. So that is to facilitate power to the system. And if we can see through this area, so here as we have discussed about this, so here you can see the connections, one from this side, another will be from that side, from back side basically, and both are with a T, it is connected here. So one of these is the backing line, one of these is the roughing line. So apart from this, we can see many things here. So see here, this is the magnetron 1 for sputter 1. So this is one of the supplies, and here this is magnetron 2 for the sputter 2. This is another supply. These are the supplies for the water, whether water is going properly or not. These are the cooling waters here. Okay, this is the first thing. Then here you can see MFCs. So argon MFC, you can see behind this there is one oxygen MFC. MFC is mass flow controller. So what it does? So we usually connect the like gas pipelines to this, and this will check as per the instructions given by you through the display or the interactive display basically. So whatever the SCCM or the amount or the volume of gas flow you want, this will allow only that much volume to be in the chamber through the pipes given. So here this argon MFC and oxygen MFC both are connected there, and you can use, so here argon is separate, and in case of oxygen, if you want nitrogen somehow, so for your process, so you can, instead of oxygen you can put nitrogen also, but MFC values will be different, that you have to calibrate it as your own. And here you can see these are the lines, these are already on here inside, because we have another regulator outside. We will operate from there leaving this area, because this will be closed during the operation. And here when just like the e-beam evaporator, we must say here that here we have all pneumatic valves. So as this is more automated than the e-beam evaporator that we had, so here you can see we have one, if we switch on the chiller unit, we will get water flow. If we switch on the compressor, we will get some pressure here, and that pressure will act as the controller of all these pneumatic valves. So some of the pneumatic valves are here, some are the outside. So after this we will move to the ports part, like how we are like how this exhaust is going out, or how we are, from where we are supplying the oxygen or argon, that part we will go to the back side basically. So we will get a zoomed in view of that just after this. Before that we will close and go. As you can see, we have closed the door, so we are now here, the other side of the tool, to show these things. So here you can see this is the air supply written. So this is the pipe that is directly from the compressor. So this compressor, I mean through the compressor we will get some particular amount of, or basically you can say a rated pressure there. So the rated pressure will be controlled by this compressor output. So we have that air supply, so that will be helpful to run all pneumatic valves. Here is the vent. So ideally we should vent with nitrogen, but as we are in a clean room, so we prefer to vent it in clean room environment only. However, for better performance or for faster evacuation of the chamber, it is always recommended to use dry nitrogen instead of air, or instead of clean room air, for venting the chamber. Here you can see the cooling water inlet and outlet both are here. So these are connected to the chiller. So through this in part, or the inlet of that of the chiller unit, like outlet of the chiller unit and inlet of this unit, you can get water of within a range of 19 to 21 degrees C, as it was in the for the other tool. And outlet is obviously little hot water, after cooling the magnetron and the chamber, because chamber outside has also the similar like similar places to or similar channels to flow the cold water. Here, as it is already written, it is rotary pump exhaust. So after the rotary pump exhaust, so it all these are connected or connected from the outside or to outside. Outside means the utility place of our lab. So that is our utility room, we have one. So that is just like a normal lab or normal place, not like a clean room environment. So after all this, we have here argon and oxygen. So inside we have already seen the argon MFC or mass flow controller, or oxygen MFC or oxygen mass flow controller. So here inside we can, I mean outside also we can see here argon is connected, because this is compulsory, because otherwise we cannot generate plasma for sputtering. Two reasons for argon: number one, it is little heavier atom first, and second, it is inert gas. So if we use oxygen or nitrogen for creating plasma, then that will react with the target itself, and we will get some different material deposited instead of that targeted material. So that's why we cannot use oxygen or nitrogen, this type of active gases, for creating plasma. So argon is used here, and oxygen or nitrogen, it will be it will use same port for oxygen or nitrogen. Before, if we change the gas, then we can flash out some amount of gas and then we can use it. However, this will be for creating the environment inside the chamber. Let us say if we deposit any oxide, let us say SiO2, then we may have to have oxygen environment in the chamber based on the recipe, or if we are depositing, let us say silicon nitride, we may have to use, or we have to have nitrogen environment in the chamber. So those things we can just make or maintain using this. So here these are the inlets and outlets to the tool that we have shown. Then we will come to the back side of the chamber. So after those ports, now we are at the back side of the chamber. So here we can see this is the turbomolecular pump. So this turbomolecular pump, here you can see one inlet water and outlet water. So this also requires some chilling, some chilled water to get, I mean use it as a coolant. So here is the turbomolecular pump. You can see it is attached here like this with O-rings and all other connections. So here you can see, I mean this is the penning gauge, Edwards, what we can show here. This is the penning gauge that can show us the pressure less than 10 power minus 3 millibar range to 10 power minus 8 9 millibar range. So we have it here. So we have checked our chamber can reach up to 10 power minus 1, 10 power minus 6 millibar approximately. So that much this chamber can reach, that can be easily covered by this penning gauge. Here is one more penning gauge, and this can, I mean, and you can see this connection is through that. So this is one of the backing lines here that you can see through this this pump and this gauge. This is the backing gauge. So here you can here if you can see, there are many ports that is possible. We can just attach some new parts to this. Now we will check it. Now we can check this thing. So this is the main controller, the pneumatic valve that controls whether the chamber will be sealed, or based on the position of this we can change the sealing or the opening of the valves. Everything will be changed here, that we can show during our demonstration. Here if we come to this top part, so here inside we have the rotary drive. So that rotary drive is to rotate the chuck after during deposition, and here we have another port that we can open just like this. We have another port. So here we can use some load lock system, so that our chamber will be always under high vacuum and we can just load our sample here. But as we are not doing that precise works, so we are using that actual chamber, I mean we are loading in actual chamber and run the tool for deposition. So this is basically outline about the tool, and here you can see inlet outlet that we have shown from the front side, and here you can see these are the channels for water coolant. So this is basic outline. So, we just checked the basic components of the tool before starting. So, now we are about to start. Before that, the last thing I want to just tell you, there you can see the back side, there is one gas connection, the regulator. So, the regulator will come to the point when we'll deposit, we'll show it in like in a closer view, because gas flow and all these things are actually important for this sputtering tool. So, from there we are like cylinders are kept outside in utility room. We took the connection here, and from there, as I have shown, that side like other side of the tool, we have that argon inlet. So, that is basically our argon connection. We will come in details, but one thing you may see, it is always in closed condition other than the time of deposition, because gas safety is also very important. Your I mean whatever the gas is there outside, it may be inert gas, but it should not be leaked in, it should not get any leakage part in the lab itself, because that can be a hazard for the person who are working in the lab. So, always it will be in closed condition. So, during deposition we will show it, we will open that in front of you and we will demonstrate the things again. So, just to start the tool, it is the same procedure as we described for the e-beam evaporator system. So, here also we will switch on the chiller and compressor first, because cooling water is important and the compressor is also important for the valves. So, we will switch on that and we will switch on the main power, and I will be back soon, like within a moment. You just hold on for a moment. So, here if you can see, the tool power is on, chiller, compressor, all these are on. Now, we are about to switch on the tool. So, as described earlier, this is the similar procedure, as you can already, I think you have noticed, this is from the same company, same make. So, procedures will be almost similar. So, let us switch it on. So, here you can see the screen, and here, as earlier also I told, after that reset can be one of the things, you may have to reset the hardware. So, we will press reset. So, after that, here you can see there is some extra option for login, because this supports supervisor mode or the user mode, engineers mode. There are many things. We usually prefer to use this in admin mode, so that we can go for any type of values, anything. So, we will just so this is to stop us from unwanted intervention, but in lab we are only using the things. So, it's I mean clear what are the passwords and all, this is already shared among us. So, here we are also showing the things, no issues with that. So, here if you see, anyway, don't go with the date and time, this is not set properly. So, here if you see, this is the manual mode. So, if we want to run the tool in manual mode, we can go with that, but this is semi automated tool where only deposition is manual, other things can run automatically. So, here even deposition can be automated. However, there is a problem. So, if any human intervention is required, that time it will create a problem. We have to stop the process, terminate it, and we have to start it again. That is why we do not prefer deposition in automated mode, but that provision is here, unlike the e-beam tool that we have shown. So, here this is the manual mode, all manual if we want to do. Here is the system control, here is the source control. So, system control is for like basic operations like venting, then loading the sample, I mean during loading the sample, whether we want to vent, then the cycle mode, or if we do other things like seal the chamber and all that, those options are here in system control. Then there comes the source control. So, in source control we have all magnetron related information like argon flow, oxygen flow, nitrogen flow, or maybe how much, I mean whether we can switch on the DTM or whether we can switch on the power supplies. All these options are here in source control. The supervisor menu, usually we do not use it as long as we actually need any changes or something. Diagnostics, diagnostics also the similar thing, and these things are all comes under supervisor menu only, because these are more like calibrating the tool as a tool with unit or time or all these things that we do not want to demonstrate also. So, what we will do, we will show like not in manual obviously, we will do it either in system control or source control. These two we will be demonstrating to you. So first let us go to system control, because see here it already sensed, because during demonstration I pressed that emergency stop once, and though I just released it, still it is showing that emergency stop pressed. So it is sensing that whatever happened to the tool. Here we will just accept that error. So whatever error will be there, that will be here, that will be shown here. So here you can see that, I mean, if somehow pressure is not enough, or compressor is not on, or water chiller is not on, so because of that, if pressure is not enough or water supply is not enough, then those like issues also will appear here. So here as I just clicked on that, you can see what are the alarms it came, that is here, or you can even see the history, when it happened, what type of problems it occurred, all these things you can see. We can just go back, as we don't actually need to check all these things now. System is in standby mode. When we just start, system will be in standby mode, so we have to start to get the pumps on. So before that we prefer to vent, because it is well known that whenever you are using any vacuum tool, always you have to keep the chamber in vacuum condition, or you have to evacuate the chamber before switching off the tool. So definitely our system is in vacuum, so we will vent the chamber, we will open, we will load some sample. This is just, it will be glass slide that is regularly available in like laboratory, or not in stationary, basically in laboratory purpose glass slides, that you are well aware of that. Once you will see, you will understand. So we will load that, then we will start deposition or the processes. So here first let us vent the chamber. So as I pressed vent, so vent is in green color, that you have seen there only when it was a closed view, and it was showing air admit valve open. So it will be open until and unless we have enough air inside to open the chamber. That means releasing that vacuum and take this to the atmospheric pressure, then only we will be able to open the door. So we will wait till that time. We are waiting now also. So here only option available is seal. So by mistake, if you start venting it, you can immediately seal it, so that you, I mean, you will not lose the vacuum. So that is one part of that. As it is almost done and we understand these things, if you are experienced enough, you will understand by the sound only when it is done, or when, or how much time it may require. As the sound stops, so so air inlet is almost stopped, so we can understand that it is already done. We will open this, and with that we will just seal the air admit valve. So now it is showing standby. Now to save our time, we can switch on the pump before loading the things, loading the sample also. So just to save our time, we can start it, but we want to demonstrate it each and everything. So first we will focus inside this chamber, we will show the things, then we will start the process there. So this is inside. Let us have a closer look what is there in the chamber. So this is inside the chamber. As I have told already, that we have a provision for deposition at a higher temperature. You can see here this and this, here are the heaters. So these are the heaters that can directly heat our chuck. So the chuck is loaded here over the shaft. We will show how to remove and how to load the things, but still here are the heaters at the two end. Now if it is in rotation, then it will definitely heat almost uniformly everywhere. So this can go up to 400 degree. Now if you can see here, one more small wire is coming out. If it is not visible, then also it is fine, no problem, because I hope you know the basic of temperature sensing. So that wire is used for sensing the temperature. So here are the things. So here now coming to this part, here you can see the similar, or before that I will just unload this so that you will get a clear view. So this is the same way we can unload the chuck. So this is little smaller chuck than that. This is 8-inch diameter, whereas that I mean in case of even evaporation tool that we have, that has 12-inch chuck. This is 8-inch only. that depends on your requirement, you procure it as you want. So here now you may get a clear view, you can see one pipe here. So this is the argon pipe. So argon flow is connected, I mean argon purging will happen through this, and here are the two magnetrons. We will come to show the details about the magnetron. Before that we want to show this. So here argon, so here you can see it is almost at the same distance, so that during deposition we don't have to open, or before deposition we don't have to open and align it properly, it is almost at the center. So argon purging will be all over, and whichever we want to use, we can use any of the magnetrons as per our wish. So when we open that down, when we open, so we have seen the connections to magnetrons. So these are here and here. So those are from the RF source or DC source. So here in this tool, this right side one, here DC source is connected, and here in the left side one RF source is connected. So we can use, or we could use this for any insulation, deposition of any insulation layer, and here this DC can be used for metals. So here, as we know that RF can deposit metals as well as insulators, so this is more versatile. But we as you know already from the theory part, that half cycle will be used for deposition and half cycle will be like relaxation things. So for faster deposition we always prefer DC for the metals, because we have that option, and not the RF. But we can use both, as presently we don't have any insulator to, I mean insulator in lab, to insulator target in lab to demonstrate the things. So we placed both the places, we placed metals only. We will just show how to generate the plasma and how to deposit it. So this is insight about this chamber. So here already what we just let us get a quick recap what we have seen already. Here this is magnetron, this is the first magnetron, second magnetron, and here is the argon flow will be through this, and here is the QCM. This is the QCM or quartz crystal monitor that we have actually shown in the EV evaporator. This is the same thing. So here is that crystal actually, and this will give the value, and we can check that through the DTM. So that much is here. So then we will just open one of the magnetrons. Let us open this only. We will just open one of these magnetrons and show different components of that. Here you can see the closure look of one magnetron. So how we are giving the instructions through the tab, or through the display, interactive display, that will show during deposition, but for now we want to show what is there inside. So first we are just removing the shutter. So you can see we can remove the shutter, that is also pneumatic. So here you can see this is one of the plates, and here is the target. So we will just take out these. So these act as the ground supply. So as I already mentioned that there will be one ground and one negative supply, and negative will be through the magnetron to the target. So here the negative connection will be there, and the other one is the ground supply, that will be through this. So while loading, this should not be in contact, like this ground and this magnetron should not be in contact. So now we have one more guard lines. We will just remove this to show you how to load or unload the this target. So all these are like Allen key based. So let us open this. Here is one point, when we are removing it, it is fine, but when we will be placing it back, we should be careful that this plate on top of the target to hold the things should not be like tilted or something. Then there is a fair chance that it will touch that ground connection that we just now removed. So those things we have to be cautious. Before that, let us remove it and show you the things like how to unload this. So here you can see, here is one groove. So this is basically here to to fix the thing, so that it will, so the target cannot move here and there. So this is the target. So here actually you can see this is the back plate is copper and here is the target. As we have used this earlier, so you can see that outside area that is still shiny and inside it is little rough, because materials from here is already scraped out and it was deposited. So with time there will be grooves, so that will be visible. This is a new target, so we cannot see that now only. But here you can see this is the magnetron. So here we will get the negative connection. So this here is the electrode, so it will come from here, and you can, with this you can manage the tilt. So whether you can keep it like this or you can exactly make it straight, those things you can change as per your wish. So here if you have this copper back plate, then transferring of the voltage or transferring of energy from the magnetron to this target will be easier, because copper is a very good conductor. So if you don't have this copper black don't have target with copper backplate, then it is better to use some graphite sheet or something on top of the magnetron before loading this target. So we are now placing it back. So we could even open after this and to show the things, but showing magnetron is not part of this course, so we'll just stop here only after showing how to load and unload the target, because we don't want to show the repairing of the tools or something. So here if we keep it here with that small groove, it may not be it may not be properly held. So this top layer is required just for that. So first we will show how to place it back. Just make sure that grooving and all things are perfect and it is properly aligned, otherwise you cannot place it back properly. So it will take some time. With time or with practice you will get more efficiency how to do this. So when loading, do not close it to its extreme first, and always try to close the Allen keys of or close the screws at the diagonal or the opposite area, just to make sure that it will not be tilted. So almost similar things you can do. So both the things you can see, and see this has a magnet. How do you understand? See this, you can see that there is a proof that magnet is there. So magnetron will work in that way. You can just place it like that. So we will just quickly place all the screws, because two are there, so we have the references now, so we can go with it quickly. So here you can see we just fixed this top plate with groove to hold the target at a particular place, and now this is the ground connection. This we will just keep it. So you have to make sure that this part is clean, otherwise this can be seen as a short connection. So before that, let us just press it. This is just like closing a container. And one thing, just make sure after you load it, there should be a gap of 2 to 3 millimeter, 2 to 3 millimeter. So this much gap, and whatever voltage you will apply, divide that by this much gap, so that much potential difference will be there, that will start breaking the gas supply or the argon atoms in ion and electrons. So those ions will be bombarding on this target, and after this bombardment, these atoms will come and fall on the on the substrate that will be loaded in the chuck. Here similarly, like if you see here, we have kept that much gap. So once it will start being in or disintegrating in ion and electron, it will create a plasma within that range. So here we'll just now let us close this. We already closed these things, and we will check the same for the other one. And as we know that we don't have any insulator, so for that RF supply we will deposit at some lower RF supply or lower power supply. And here we as this is tungsten, so it is hard material and it is high melting point material, so it requires some higher uh, power, DC power. So we will see all this. Before that, we will load the sample, on sample on chuck, and we will load it here, and then we will close the chamber. So let us go to our solvent bench where we will be loading the sample. So I have so this is the chuck. I have placed it here. So there is actually no particular reason of placing it here. If you want to, based on your application, you can keep. So here you can see impression of on 4-inch wafer. Earlier we deposited, so that impression is still here. And after one deposition or two depositions, you have to clean the chuck. So here you can see that normal glass slides. I have just pasted one. So now we'll fix it with Kapton tape, and in a single go we will deposit both the materials, because here we are not actually targeting any particular device to fabricate. So deposition is not, deposition is important for demonstration purpose only. So we will demonstrate DC sputtering as well as RF sputtering both in same round. So let us just, we will just create some pattern type thing so that it will be visible to you in a better way. Okay, so we are just sticking it, so you can see one sharp edge hopefully after the deposition, that we want to show you. So before deposition, just make sure it is properly attached, so that it, during deposition, when we will go for rotation, like we always prefer to deposit under with the rotation. So when we will go for rotation, it should not fall on the target or it should not fall in the chamber. So for that you should make sure it is properly connected or properly attached. So let us go with that. So now we can see it is attached with some typical pattern that doesn't have any significance, but we just did it like that. We will show how this deposition happens. So we have the chuck here, we will just place it. This is the same process, so close up view is not that important. So you have checked already during e-beam evaporation similar loading process. So here when we are loading it, as we will be depositing in rotation, so it doesn't matter where we are actually loading the sample. Otherwise, based on the magnetron, we had to load it properly so that it can exactly come above one of the magnetrons, that is our targeted magnetrons, like either this or that. But here, as this is just like deposition in rotation, and as this is just a demonstration, we will deposit both the materials on same sample. So we are just loading it here. Now if we have anything to see, or whenever we want to see whatever is going on inside, we can always use this viewport. So we will show it here. So here you can just open the viewport and see what is going on inside. As magnetron is set properly, all the both the covers, it is already covered by the shutter here, so it will not deposit directly on this the substrate on this. So now it is good to close and we will start evacuation process. So when the vacuum will reach, we will again start the deposition. So let us come here. So here we are in system control window. In this monitor you can see either you can start or you can vent. There is no point of venting because already the chamber is in atmospheric pressure as we just loaded, and we can see here backing pressure is still lesser than the atmospheric pressure because we are not, we did not open those valves. So we just close or seal the chamber and opened it. So that vacuum is still remain. Now we will just start, so that pump will be started. After that we will come back to each of these points. Let us start the pump. So it will take some time, as you can see already that backing pump is starting now. So when after some amount of backing, when there will be some safe pressure for the turbo to be on, that time turbo will start and it will be on and it will show, see it is already showing turbo pump ready. So now it will take some more time to get the cycle command. So after that we can go for cycle. So now you can see with turbo pump ready status, cycle is also glowing. So now we can go for creating vacuum. So vacuum cycle is anyway it is automated. So when we will start, we can discuss other things as well. So it will start with roughing. So backing valve will be closed, roughing valve will be opened and it will start roughing. See, it already started roughing. So in roughing step, it will first create or it will evacuate the chamber as well as the roughing line. So after that it will be to the backing line, because see backing pressure is always less and your turbo is on, so that cannot be exposed to atmospheric or near to atmospheric pressures. So it is duty of the turbo line to get that evacuation. After that only backing will start. We can just get one better idea about this process from this system view. If you see, this is the, this is the chamber. Here these are two magnetrons and here there are the connections, like one MFC is dedicated to argon and the other MFC is dedicated to oxygen only, but you can use nitrogen as well, anything you can use here. And here are the other gauges. There are two Pirani gauges there, and here one of the valves that is like for inlet, and here if you see this is like inlet means this is vent valve, and if you see here one is this backing line, one is this roughing line. This is the roughing line that is on now. So roughing valve is on and through this rotary pump that is on, it is getting evacuated. And again after some time, so high vacuum valve will be on and backing valve will be on, and through this, through turbo, it will take over with time. So when backing pressure and these things are going on, we can just go back to check the status. This is the basic system view. So after this, this will be stopped, or this will be 3, or the roughing valve will be closed, backing valve will be on, then this part is already under vacuum, still it will just like a cross check, it will check through this Pirani valve, whether Pirani gauge, whether it is proper, and then it will be exposed completely through this high vacuum valve. Let us go back. So here when roughing is going on, we can just like extend the discussion a little bit. So here main menu, you can go back to that previous like menu where system control, source control, everything will be there. Then you can come here system view, that you can that we already checked just now. Now source control. Now the source control you can access it from the main menu as well as from here. The source control, as I already discussed, it will have all the information about this magnetron, like RF power, DC power. These are two magnetrons, and this MFC or the mass flow controller, you can control how much gas will be flowing, and here magnet and shutter, whether to close or how to close, open, everything is here. DTM is here, and backing pressure, roughing pressure, all these things, all this information you can get here will come in detailed discussion when we will deposit the thing, I mean deposit the materials. So here and here SCC control. So from here this is basically accessories. So here you can check, or you can start rotation of the chuck, or you can use heater. So these are the basic features that we can get here. Let us go back to system control here, so that after roughing we will see till high vacuum valve is on, or it will start high vacuum like cycle. After that we will take a in offline we will just create the vacuum, then we will come back for deposition again. But till that time just wait, hardly it will take few more minutes from roughing to backing to this. So here you can see it will be almost equivalent pressure, that time it will be shifted from roughing to backing, or roughing line to backing line. So before starting the process you can just go back and check the theory classes for a better idea. So here actually you can see this is showing now the chamber condition. So like see, this is 24, whatever is in red, that is basically whatever temperature, whatever is the temperature sensed by the temperature sensor placed inside just on above the chuck. So in the chamber where our sample is loaded, that temperature is 24 now. So as of now this is the set temperature that in last deposition we have used, that is 100 degree C. So this 100 degree C you can increase, decrease till 400 degree C you can go, that is up to the scope of this tool. So here we are using, or we used 100, but when we will deposit it or demonstrate it now today, so we will not increase the temperature because we are depositing metal only. So it is kind of useless to use this heater or heat the chamber inside. So now this before heating we should think of what type of material is loaded there. If there is any polymer, then we should check whether that polymer can sustain up to that level or not. That is one thing. And then whatever and the second thing, obviously what material you are about to deposit, the temperature is important or not. Like let us say some material may need 200 degree C for rearrangement, or that is like some short annealing also you can tell. But if you cannot reach that temperature, then there is no point of doing it. So these are the few things that you can get a better idea whenever you will just go through the theory part once again. So you can see still roughing is going on, we are waiting for that. So here you can see now backing valve opened just now. So after that much of roughing, now it is pump down status, and I think you can get the sound already. So it is pneumatic valve. So while changing from one state to another state, it will I mean you will get that sound because of the pneumatic valve. See, now it reached to fine pumping. Fine pumping means through the backing line, now it is getting pumped or evacuated by the turbomolecular pump. Just for a confirmation, you can just check here the system view. See, now this is closed, this wrapping line is closed, and high vacuum valve and backing valve is open. So it is creating vacuum through this. And if you go back, you can see that now you can seal the chamber, you can process, you can start process at this pressure, or you can vent the chamber as usual. And we are not doing any venting thing here. So we will wait till this reach e power minus 6 pressure, then we will show deposition of the materials using RF source as well as using DC source. Okay, so let us wait for some more time till it reaches e power minus 6. Usually prefer 3 e power minus 6 or 2 e power minus 6, but thing is you can actually deposit at any pressure below 5 e power minus 6 practically, but as we have the capability of the tool, so we will just wait till 3 e power minus 6.